This screencast is about being able to graph linear inequalities and a special form of those, absolute value inequalities. Let's look at a couple of terms related to linear inequalities. Of course, a linear inequality itself is a function that is only true when the conditions in the statement in the inequality are met. And the key to that is graphing the boundary, which in the case of a linear inequality is a line. It's a border line that separates the true from the untrue or false regions of the inequality. So there's two halves of it. One half, and they're called half planes. One half plane is where the conditions of the inequality are met. The other half plane is where the conditions are not met. Here's some general guidelines on how to graph a linear inequality. First of all, we're going to graph the inequality boundary, just like we would a linear equation. The difference here is that we're going to draw either a solid line if it's less than or equal to or greater than or equal to, or a dashed line if it is just less than or greater than. That's because a solid line will indicate that the boundary is part of the solution. A dashed line will indicate that the boundary, still a boundary, but is not part of the solution to the inequality. Next thing we'll do is test a point that's not on the boundary. I like to use 0, 0 because it's simple to substitute, but if 0, 0 is on the boundary, we can't use it. If that test point satisfies the inequality, in other words, if it results in a true statement, we're going to shade the half plane that that point lies in. If the point fails the test, if the inequality is not true when we substitute the coordinates of that point, then we're going to shade the other half plane. So let's look at an example. We're going to take the inequality x minus 2y less than 4. That's in standard form. So the boundary is going to be the line x minus 2y equals 4. So let's go ahead and graph that. We would do it using intercepts. The x-intercept is going to be where the y-coordinate is 0, so that's at x equals 4. The y-intercept is going to be where the x is 0, and so that's going to be at negative 2. So those 2 points will help us graph this boundary line. It is dashed because the defining symbol of the inequality is a less than. So therefore, this boundary line is not part of the solution, but it is still a boundary. Next thing we're going to do, we're going to test a point. Again, I like 0, 0. Why? Because it's simple. We're going to put 0, 0 into this inequality. If I put in a 0 for x and a 0 for y, I get 0 minus 0 less than 4. 0 is less than 4. That's a true statement. Therefore, the origin, 0, 0, is in the half plane on the top half of this boundary line. So what I'm going to do is shade that region that contains the test point. And so every point within this half plane is a solution to the linear inequality x minus 2y less than 4. It's important to note that the boundary line is not part of the solution in this case because it is just a less than. Okay, let's look at an example. A tutoring company advertises that it specializes in helping students who have a combined score in the SAT that is 900 or less. So we're going to write an inequality to describe the combined scores of students who are prospective tutoring clients. We're going to let x represent the verbal score and y the math score, and we're going to graph the inequality. And so we have to write it as an inequality first before we can graph it. The total combined from the verbal and the math scores, x and y, must be 900 or less. So this kind of breaks it up into parts. So the verbal part, x, and the math part, which of course is more important, y, is less than or equal to 900. That's how we write that as an inequality. So what we're going to have to do first is graph the boundary line. The x-intercept is 900, the y-intercept is 900. So when I combine them together and I get this boundary line, I plot the boundary line, I use an x-intercept of 900 and a y-intercept of 900. And it's a solid line because of the less than or equal to, because of the equal to part of that. And so I'm going to test the point 0, 0. Well, if I put in a 0 for x and a 0 for y, I get 0 less than or equal to 900, which is a true statement. Therefore, 0, 0 is part of the solution, and that entire half plane below this boundary line is true. Now, I'm really only interested in scores in quadrant 1 because there can't be negative SAT scores, so it's really this triangular region. X plus y equals 900 is the boundary and is part of the solution. Everything here in pink is also part of the solution. Any scores that represent those combinations will work. So does a student who gets a verbal score of 480 and a math score of 410 fit the tutoring company's guidelines? Well, let's plot the point 480, 410 and see what happens. So if I go 480 on the x-axis, which is about here, and then I go up 410 to about this point right here, that point is barely in the shaded region, but it is. So this student does fit the tutoring company's profile. So let's look at graphing an absolute value inequality. Very much like graphing an absolute value equation, it is, in this case, we're graphing y greater than or equal to absolute value of x minus 2. It's a greater than or equal to, so our boundary line of this function is going to be solid. And so we're going to graph the equation y equals absolute value of x minus 2 as our boundary. Well, how do we do that? Well, go back to our transformations. We have the parent function of the absolute value, which is that V sort of shape. And then we're shifting that down by 2 because we have the minus 2 there. So in the end, it's just the absolute value graph shifted by 2. So this is what the absolute value of x minus 2 as our boundary line looks like. So next thing we're going to do, we're going to test a point. Since 0, 0 is not on the boundary line, we're going to test it. And if I put in a 0, 0 into this inequality, I get 0 greater than or equal to absolute value of 0 minus 2. So it says that 0 is greater than or equal to negative 2. That's a true statement. Therefore, we're going to shade the part of the plane that includes our test point of 0, 0. So this area that's above this V, if you will, is the solution to our absolute value inequality. In this screencast, we learned how to graph linear inequalities to include those involving absolute value.